Hey guys, welcome back to AlgoYogi, and we are doing trees series right now. Doing the medium level LeetCode problems. Let's go to our next problem, which is check completeness of a binary tree. Let's go to LeetCode. Problem description is quite simple. It's we're given the root of a binary tree. We need to determine if it is a complete binary tree, and we will be returning a boolean value. If it is complete, then we return true. If it is not complete, then we return false. And so what is a complete binary tree? I guess you guys can check out my main tree conceptual video to find that out, but we're gonna find that out right now as well. So in a complete binary tree, every level except possibly the last level is completely filled. However, even in the last level, it's not completely filled, but all the nodes should be aligned to as left as possible. So let's see a couple of examples. So in first example, we see at every level, level 1, level 2, and level 3. Since it's a binary tree, now starting with first level, the number of nodes is 1. Second level, it's 2 because one node has 2 child left and right, and they're both completely filled in our first example. But if you see the third level, here we're going from left to right in our level order traversal. There is no node that is missing a value before it's filling a value that should appear before it. So what I mean to say is, in the last level, if we see 2 has 2 nodes, basically 4 and 6. So these two position, left and right child of 2, they're both filled. And for 3, left needs to be filled first before we fill right, which first example has done correctly. And the last position, which is the right child of 3, can be missing, and that's in the definition of complete binary tree, that in the last level values in right don't have to be there. It's just from the left to right we need to fill all the positions before we even move to right. So we can see some examples which are not complete binary tree. So another example that we can see is similar to example 1, but just instead of filling this last level from left to right, we decided to skip a value and then we add 6 over here. So this is what we are missing this time. This is what we are missing. So let me remove it. Now this is not a complete binary tree. Why? See, all the levels are filled. Level 1, level 2. In level 3, we see there are two values. However, there is a position where one of the node is missing from left to right, and the value there is null. So our approach to find out if binary tree is a complete binary tree is going to be very simple. We'll use BFS, breadth first search, which is basically going level by level. So starting with root, level by level we are traversing, and then at a given point of level, what we're going to do is we take the snapshot of that particular level. So let's say this level, we take this snapshot and we see, and this time the only thing is we will be adding null values to our queue. Queue is the data structure that we use while running our algorithm, BFS algorithm. So we use queue data structure so that it's first in, first out. So we process the node as we receive them, like from the parent node. And then we have 6 here. So this is the place where we have this missing node, null, and that is the reason this is not a complete binary tree. So we can do it, and there might be some cases where the last level, sorry, is completely filled. And let's say, for example, I'll just create a small example for that. So here the value of the node doesn't really matter, so I'll just place X over here. But in the example, you'll see why this is not a complete binary tree. So if you see this one, the last level is not the only level that has to be, aligned with the definition of complete binary tree. It's you have to check at every single level if they fulfill the definition, which is every level has to be completely filled, which is not in this case. This is not completely filled, so it's not a complete binary tree, although the last level here does satisfy all the conditions of a complete binary tree. So I think the solution will be quite simple. It's just we have to understand the definition right, and just transition it into our code. Okay, let's move on to our code editor and write the solution down. Okay, let's write our solution. Let me focus on the editor. So we're going to have a queue. I'm going to use a stack to track the route, so that will be our route. We're going to have a flag to check if we have seen null values between two non-null values. So that will be seen null. Initially that will be false, and then I'll have a while loop for seen null, not seen null, like q, sorry, my bad, for q, and I'm gonna pop out the node q dot pop, that's from 0. If you're using dq, that will be pop left, but here I'm just using its normal array, so that's just, or a stack you can say. So it's simply popping from the front, appending in the back. So if node, that means what? I want to check if I have seen null before. So that means if my current node is non-empty and I have seen some null, then I return false. Okay. Otherwise, I will add to my queue left and right child of my current node. So q dot append node dot left and q dot append node dot right. Otherwise I have basically seen some none values. That means this is null. So that means what? I have seen null, and I can just mark it true. Otherwise I can return true. So let's run it. Awesome. Let me zoom out so you guys can see, and let's submit it. Okay, let's write the time complexity. Sorry, my bad. Time complexity here would be big of n, that's the number of nodes. We are visiting each node just one time. And then space complexity will be basically big of n as well. That's the maximum number of nodes we are storing in our queue at a time. All right, let's go back to AlgoYogi, mark this problem solved, and see you guys in the next problem. Bye bye.